Okay, next speaker we have is Vicki Colvin, who I have heard speak, and she really has wonderful perspectives to share with us. She's a vice provost at Rice, and she's director of the Center for Biological and Environmental Nanotechnology. She's a professor of chemistry, chemical, and also biomolecular engineering. She focuses her research on nanoscale particles and environmental living systems, and she has a lot to share with us.
Well, thank you, Carla, for inviting me. It's been really inspirational. I love conferences where you hear a lot of different things from different areas, and it's also great to be surrounded by so many fabulous female scientists. So that's been really great. So while my presentation is going, I'll try to do my introduction. So I think the title I got, which I love getting a title now that somebody's given me one, was, sort of how do you put nanotechnology, chemistry, and engineering sort of out in the world. And that's part of what I do. So I've been doing nanotechnology since, actually I was an undergraduate as an RAU student many years ago. And I've seen the field sort of go from nowhere, before country was cool, to being, one of the largest interdisciplinary areas certainly funded in the United States. And so as I've seen that trajectory move, it's amazing the capabilities that we've developed to make really small nanoparticles and nanomaterials broadly. And so really what's happening in this community now is an interest in beginning to transition that into the real world. And that real world has a lot of different facets. Obviously, it might be our country. And if my presentation would come up, I could show you some examples in a second of some of the products you might use. For example, do you know any products you use daily that would have nanoparticles in them? Anybody? Makeup, yes. Another one? Yes, what? That's right. Rackets. For some reason, you get a lot of carbon nanocomposites in things like golf clubs and bicycle frames. A more exciting example is the new Boeing Dreamliner. The carbon composite material isn't quite nanoscale carbon in there, but it's very close. And so that allows it to be much more lighter weight and withstand greater pressures, which is, I haven't been able to be on one yet, but one of the reasons it's supposed to be so comfortable. So, over this almost 30 years now of activity and probably focused decade of investment by this government, you're really seeing these things begin to actually become applied in real ways. Can I help? I'm really stuck without. I've once in my life had to give a presentation without slides. And it was probably one of my better presentations, I must say. Okay, I'm going to start my timer.
Is the power for this one? Because you're using Lenovo, so I don't have the power.
I won't need power. It's totally charged. Just plug it in and we should be able to go. Okay. All right, so okay, there we go. Now I have my crutch. As a chemist, chemistry I think is one of the most visual sciences. We can argue about what's the most visual science, but I think chemists in particular are driven visually. So we need our pictures. So let's see. I'm trying to decide how many slides I'm going to cut out. Okay, yay, all right. So the PS is what's interesting. As you take nanotech into the real world, I'll give you two examples. It's hard. And some of the reasons it's hard are going to resonate with some of the themes that we've heard today. Okay, let's see if this works. This is not, is this plugged in? Boy, this is just, okay. All right. Well, I can give you hand signals, but I'd rather, yeah. Do you have another one?
No, because I have plugged in here. So.
Is it a laptop?
I just plug in, so it may take a while.
Okay, well, next slide then. And just hit it, yeah. Okay, so this is my favorite picture in the world next to the pictures of my children. And the story behind this picture, since we've had a lot of picture stories today, is that this is a particle that I made when I was a graduate student. And what you're looking at, why I think it's a beautiful image, is that it's really showing you what nanomaterials and nanotechnology are all about in a single picture. So the columns, the white dots here are columns of atoms in a nanocrystalline lattice. And so the whole thing is about 6 nanometers across, or 60 angstroms. And so if you're a biologist, lysozyme is about that big. So it's bigger than a lot of biological systems, but way smaller than a cell. So the ability to interact with living systems is pretty remarkable. Another thing that's really amazing about the image, which is a TEM, so you're projecting electrons through this 3-dimensional object, and the model background here is amorphous carbon that holds it in the electron beam, is that it's perfect. It's what's most striking is that the atoms are in exactly all the right places. And that's actually what makes nanotechnology so special. When we make our materials, we don't just make them small. We have to have the atoms in very specific, they have to be crystalline, or in the case of nanotubes, in a graphitic lattice. And if all these atoms were disordered, it wouldn't do most of what we want it to do. And that's been what a lot of the chemistry has been working towards, is how do you make little tiny pieces of material, because you pay a pretty big thermodynamic price for what's obvious also in the picture is that this crystal terminates. It doesn't go on forever. So it has to have a coating on it that helps it integrate with water or whatever other environment you might put it in. So should it work now? Yes, okay. So it's small, it's perfect, and the fun thing about it is that it's strange. Nanomaterials are valuable because they have weird properties. So these are now pulled out. You're seeing a zone of a whole bunch of nanoparticles. And these are about 3 nanometers in diameter, and these are about 30 nanometers in diameter. And the obvious difference, if you stare at it long enough, is that for the same weight of particles, when you're smaller, you have higher surface area. So that's one of the reasons you go tiny, is in a gram of particles that's 3 nanometers, let's say silicon dioxide, you probably have the surface area of this room. And if they were even 10 nanometers across, you'd have the surface area of this corner. So if you need a lot of surface in whatever you're trying to do with something, it's good. But that's actually the boring part of nanotechnology, just the surface area. It's important, but it's not really what got most people into the field. What really drives us is the fact that when you make them tiny, you make them strange and different than bulk materials. And you should take a moment, and if you haven't thought about nanotechnology recently, how weird that is. We think of aluminum or gold as a metal that has a color, certain properties, i.e. not very reactive. But if you make it nanoscale, gold is one of the most reactive oxidative catalysts we know of. And that's because size matters. How many atoms you have in a substance can very often fundamentally change its optical, mechanical, physical, chemical properties. This particular example, near and dear to my heart because that first picture was a quantum dot, shows 3 nanometer cadmium selenide, same stuff, 3 nanometers, about 800 atoms, all the way up to 6 nanometers, twice as big. It's got actually many more atoms, several thousand. And you see the color changing, both in absorption and emission. And that's actually the confinement of the optical excitations by the edges of this crystalline lattice. So what you're doing in nanotechnology is giving us a new knob, materials producers like myself, and saying, okay, you can make cadmium selenide, but now you can tailor it to behave in very particular ways based on its size. And that's usually when you get the most amazing technology out of the system. And I'll just show you a recent data set from my group. We do a lot of environmental work. This is Daphnia, a water flea. If you put nanoparticles in water, most aquatic organisms ingest them. And so you can see this picture of it eating the nanoparticles, and they do come out. And what was interesting about this study is you'll see these color on top. You can actually monitor that over days. These are highly emissive. You can actually buy similar things from Life Technologies for biomedical tagging. But that's actually the nanoparticles getting hung up in the goo of the Daphnia. Most aquatic organisms have gooey exteriors that they develop to recruit nutrients, and nanoparticles get caught up in this. And so as you think about bioaccumulation and how do nanoparticles move through ecological life cycles, what's interesting is unlike a little tiny molecule, which doesn't get caught up in the goo, nanoparticles can, and it gives you a whole new route of both biomagnification and bioaccumulation. And you can visualize it and watch it and study it because you have quantum dots that are highly emissive, and in fact you can do different sizes and all kinds of cool stuff. The other thing you can do with nanomaterials, like I said initially, is new products. There's a lot of reasons to think that some of the projections about the nanotech industry might have been conservative. You'll have products that really not get you super excited, like sunscreen. You'll see others that are coming out in the alternative energy space, and certainly nanomedicine, as we heard earlier, a really great example. But the real question is, can we take the sort of application of nanotechnology in our high-tech society and think about going outside of our high-tech society and solve some of the global problems that we have to face? And that's really what motivated me to start this project that I'm going to tell you about right now, and that's a water-based project. So the problem we went after was arsenic, partly because if you want to help a lot of areas in the world, arsenic's a big problem. Most people think of Bangladesh, but in fact it's a huge problem in Mexico and also in the northeastern United States. Most water treatment systems don't remove it, and it's got one of the clearest epidemiological relationships to bladder and kidney cancer of any known toxicant. So you can predict bladder and kidney cancer rates based on the amount of arsenic in the drinking water supplies. So it's a really good thing to know how to get rid of. And it's extremely difficult to do. These are some examples. I won't go through the technologies that are out there. But to make a long story short, the chemistry of arsenic, in solution it's actually an arsenate. Arsenic's in the middle with oxygens around it. And it's really, really big and diffuse and anionic. It's hard to get to stick to stuff. And so many of the existing technologies have been very poor, very inefficient. A lot of material, not a lot of arsenic stuck to it. But one that was getting a lot of interest was this red mud material, which is actually mine tailings, which has a lot of iron oxide. So for other reasons, but these are examples of some of the materials that we would make, different sizes. This is actually commercial iron oxide sorbent. The difference between this example and these examples are two things. These are highly crystalline, and going back to that surface area thing, they have huge surface areas. So potentially we could trap a lot of arsenic onto the surface of the particles strictly by the surface area effect. So I worked with my environmental engineering colleague, Mason Thompson. These are some examples of absorption curves where you expose the materials to arsenic and you watch how much gets absorbed. There's some very interesting chemistry here. But to cut to the chase, it worked as we expected. We found absorption capacities in excess of 12 weight%. So in 1 gram of one of my iron oxide powders, we could get 120 milligrams of arsenic, which is a really, really high number and starts to look practical in some ways. Our biggest problem was that nanoparticles are so small, when you put them in a solution, they don't come out. So say I have a solution of nanoparticles that's, arsenic is sticking to. Great. How do I get rid of the particles? If I use a filter, the filter sizes are so small that the pressure I have to apply is like huge, and you can't imagine doing it, particularly in a rural environment. If you want to try to sediment it, well, you'll have to wait a couple of million years. Nanoparticles are very, very small. And in fact, sedimentation rates are exquisitely sensitive to size. So at this size range, they don't come out of solution. So I got enamored. In fact, my students were making fun of me because the Star Trek beam, the tractor beam, how it can hold things and pull them around. So the basis of that science fiction technology was EM. You would apply a field, it would attract something, and that's how you would control it. So magnetic separations were known. Larger magnetic particles, a lot of you probably have, if you're biologists, have worked with magnetic beads. But ours are smaller, same idea. You have magnetic particles, you put an external magnetic field, just like a fridge sticks, magnet sticks to your fridge, it sticks to the sides, the water comes through, which is clean, and then you turn off the field and you collect all your particles that have your bad stuff on them, and you go and figure out some way to concentrate it even further. So I just loved this idea. So the thing that really got me and got my students was this equation. It's sort of a tyrannical equation, but it describes the force acting on a magnetic particle in the presence of a magnetic field. I won't go through why and how this equation came about, but I wanted you to notice two things, x and v sub p. We haven't seen an equation yet, so I thought I would keep it in. This is what kills you. As you make something smaller, you get a lot of surface area, but you also diminish its volume. And the force that acts on the particle depends on how big it is. So as you get tinier and tinier and tinier, your force goes down as r cubed, and you can't beat thermal energy. So the prediction that has actually stood for 3 decades, it was a guy called Cotton back in the 70s, said magnetic separation is great, but forget it for particles under 50 nanometers. Can't do it, they won't move. So, I was very depressed, and I stared at the equation. We talked a lot about how to get around it. And then one of my students went out and bought an immunoseparator system and actually found that our particles did move. So, in fact, they move at extremely low fields. This is not quite a fridge magnet, but it's not a lot larger. And this observation was a surprise, and it's always fun in science when you're surprised. So I'm telling the story in the surprise way rather than I expected it way, as I sometimes do. In any case, so we saw this, and we're scratching our heads, why is this? And the reason is kind of cool. It really emphasizes why nanotech, why you work with small particles. It's because they're different. So as particles get very, very tiny, they have fewer spins. And what that means is when they're really small, they're crummy magnets. They don't have enough spins to even interact with an applied field very effectively. It's called a superparamagnetic regime, and they actually cannot hold on to an internal field. If they're really big, hold in your hand kind of materials, they actually have a lot of magnetic domains. Their spins align, but not all in the same way. So if you summed up all these vectors, it's kind of small. So they're okay magnets, not great. But just in the sweet spot, just like Goldilocks, You're just right. All the spins can exist in one direction, and that's called a single domain magnet. And it's an amazingly strong magnet for per unit volume. And so this term susceptibility, which is how good of a magnet you have, goes up several orders of magnitude in this sweet spot. And that was the argument we put forward. Luckily for us, nature backed us up. This is a beautiful picture from Stefan Mahn's group. Does anybody know what this is? Some of you will. It's a magnetotactic bacteria. So when nature wanted to make small iron oxide particles all by itself to interact with the Earth's magnetic field, guess what size nature made them? 20 nanometers. That was the perfect size. These are not larger, and they're not smaller. So magnetotactic bacteria range in size. The natural magnetite is highly magnetic. It's about 15 to 20 nanometers. They are also chained, which increases their ability to add their moments together. So that was sort of the basis for why we think we saw our effect. We had particles in this sweet spot. So that allowed us to go from magnetic separators that you plug into the wall that apply 2 Tesla to magnetic separators that have no power required. And in fact, this is a hard drive magnet my students scavenged from an old computer. And that's got enough oomph to pull them out of solution. So there we solved the getting them out of the solution problem. And in fact, it works pretty well. OK, so we decided to try to do something with it, which is the hard part. So for a variety of reasons in Texas, I have a history of having a lot of Hispanic female graduate students, which has been wonderful. They're really fabulous. Gone on to do wonderful things. And so they wanted to, go to the field, and we talked about a few places. And it turned out Guanajuato, Mexico was safe, not too far from Houston. It's a plane trip. And in fact, for a variety of reasons, I happen to know the guy who ran their local water treatment facility. So it's not quite rural, but it's a situation in which this basically desert sort of city cannot use groundwater because of arsenic contamination, and it's limiting their water supply. So it's not a public health issue, but it was a good set of test sites. Our first problem that the students faced is, so we went there, we were trying to do a field test. We're going to have to build a big magnetic separator filter thing. But the problem was the amount of material. So it's not a very big town, but at the typical numbers we had, 50 ppb arsenic, it's actually more like 100 parts per billion. Generally, it depends on if it's rained recently. What we found is that we needed 11 metric tons of stuff, which is way beyond what we could make. Luckily, I'm not joking, there's an Israeli company that makes black food coloring powder that is, in fact, nanoscale magnetite. So we're going to buy some of that initially, and some of our work was done with that Israeli black food coloring, which was very convenient because we're allowed to put food-safe ingredients into water treatment trains. But the problem was really this. We needed materials, and my students were smart. This time they were very much more smarter than me. In fact, Jafar Yavuz, who's now our professor in Korea, decided to make it in a kitchen. He calls it the kitchen synthesis. So he figured out our starting material is iron oxide, actually. We dissolve iron oxide, which is rust, and we reprecipitate it as nanoparticles. He converted olive oil into basically oleic acid through a saponification process. And then you add, I'm not joking, diesel oil. And you put it all. He initially used a deep fat turkey fryer. It was in a hood. It was very safe. Here he's using a pan. And he does this reaction. Now, you got to know in my lab, it looks like, big chemistry, Schlenk lines, and really expensive chemicals go into this. So I was stunned when he said, we made great stuff. So I'll show you what we made. So with diesel oil diluents, depending on how much diesel oil we added, here's the particles we got out. We got really uniform stuff. And in fact, we kind of like these particles for a little bit better reasons. The reaction fails, the material isn't magnetic, doesn't separate, we just plow it back in. So we had a route, and in fact, there's a local company now that's doing this. It turned out it got picked up by a company that makes ceramic pots, interestingly enough. So, okay, so we had a way to make it locally, which was huge. It took a couple of years. And here's the kinds of things we did. We did batch experiments, columns. We did some sand filter work. And this is actually an example of a well in the field we attached filters to. Sometimes we work with tanks. Sometimes we try to work directly off the wells. And we looked at a lot of different materials. And Jesse Farrell, a really great guy who now works for Schlumberger, was one of the lead students. And I called it the MacGyver engineering and chemistry. You needed to put nanoparticles in a column in the middle of nowhere. Luckily, they had a Home Depot. OK, so this is the kind of data we get. And I'm not going to tell you about all the cool stuff and chemistry that goes on here. What I want to say is why it was hard. So we're still there, and it's taken us about 6 years. So what was hard about trying to go to the real world, besides incredibly tough chemistry to deal with, is the Mexican politics. So my friend, it turns out, was the director of the water corporation for the city of Guanajuato. His brother was the mayor, but they only served 2 years. And man, we started like 6 months before his brother became mayor, so we were treated to everything in the city. We could have any amount. And then all of a sudden, his brother wasn't mayor anymore. In fact, we had to move to another city called Salamanca, which now we only have 2 years to function in, because when they change over the government, they want to pick a different group of Americans to associate with. So one of our big issues has been this Mexican politics issue, which I'm still trying to figure out. But we weather it and try to make friends as much as possible. And the second problem that we've faced is our academic culture. You know, I'm a scientist by training. I'm a physical chemist. And I have had a heck of a time engaging engineers, real engineering professors, because they don't consider this academic research. So it's great for my students. They have a great time. They learn, I think, an enormous quantity. And this isn't their whole thesis project, but in some cases can be a lot. But really, there's a big disincentive in academic engineering into sort of going into the field because it makes it too applied. It's a very interesting dynamic. So I've been fighting that with my colleagues, and you can then imagine the difficulty in getting papers published and grants. But those are really the things that I think have made this really hard. Okay, I've got a few minutes left, so I'm going to go to another real-world issue that's very different, but consumes a lot of what my lab does, and that is eco-responsible nanotech. It's a shorter story. So the idea here is if you're going to go to the real world and build up nanoparticles at huge scale, you don't want to have another environmental disaster. I mean, chemistry, nobody wants their kids to be a chemist. If you take a survey and ask parents, what kind of scientist would you like your kid to be? Chemistry is usually like really low because we pollute. We make bad chemicals that pollute the world. And chemists can get very angry and say it's not their fault, but I actually, as a chemist, I can lay the blame at my own feet. Actually, we should think ahead. We should try to be proactive with new materials and ask, what could the consequences possibly be? So rather than just talking about all the good stuff our new materials and chemicals can do, I think it's super important to simultaneously consider what we call the dark side. All the bad stuff one could imagine. So if you're going to blue team your science, you should also red team it. And this has been a very important part of nanotech and has actually been well supported by our government. So there's a lot of research here that I'm not going to go into. I just wanted to touch on it because there's some interesting points to make, maybe as some of the themes that we've come up with today. So this idea is if you had tried to find out that DDT would be bad while you were making it, would you have figured it out? And I think you would have. I don't think it's that incredibly hard to think through possible consequences. You may not get the right one, but you can at least look for it. So what are nanotechnologists in the environmental nanotechnology community doing? Well, this is a life cycle of a nanoparticle. So if you want to minimize its impact, you have a bunch of different places you can try to intervene. Of course, you can try to change the whole nanoparticle, which is actually pretty extreme, to try to make it not have an effect if it does. Or you can do a lot of other stuff. So you can reduce the surface reactivity of nanoparticles. So a lot of nanoparticles, like those quantum dots, by the way, they're used in LEDs you can buy in Lowe's right now. They contain cadmium. So if they go into the environment and a fish eats them, the fish is going to get sick if he eats enough of them. So if you can somehow change the cadmium or use a different surface coating, you can sometimes minimize that. You can change the biological association of nanoparticles, or you can simply contain and reuse them, as we try to do in the magnetite process I just described. But one example I wanted to highlight, because again, this is kind of a story. So I'm at Rice University. It's fullerene central. And so I'm surrounded by a lot of great carbon nanochemists. My background is more inorganic chemistry. And these are the two classic C60, which I'm sure you guys have seen. This is actually looking end-on a nanotube that's got a surface coating. So you can have a tube of carbon, you can have a ball of carbon. Both of them are really great materials, many, many, many wonderful applications. And my initial thought when I started to think about the environmental impacts of this stuff was, oh, it's not going to do anything. It's going to be deader than a doornail. And my logic, or my hypothesis, was these are extremely hydrophobic. They're some of the most hydrophobic molecules you know how to make. And you can't get them into water. They don't really go into water. So as a chemist, I'm like, well, if they don't go into water, how can I even dose a cell? It won't even happen. So interestingly enough, it's our group and many others started to look at these materials and kind of some screening tests. This is a little bit hard to read. This is a minimum inhibitory concentration against bacteria, a lot of different nanoparticles. And traditionally, the fullerenes would come up low. They would have the biggest impacts. And this was also repeated in a number of cell studies, and there's some very interesting mechanisms here. But I want to focus on one of the key mechanisms because it sort of, I think, is defining a little bit how our field is thinking about minimizing impact. So this is actually a picture of a bunch of human durable fibroblasts in cell culture that have been treated with fullerenes. And these materials were to very low concentrations, part per billion in the solution, and they were soluble at that level. But over time, you start to see them associate with the surfaces of cells. And in the upper right corner is an AFM. This is a case with fungi. Any organism you put them with, they go and they actually, these are large aggregates, but they interpenetrate the membranes. Because they're so hydrophobic, the concentration partitions into the most hydrophobic regions of organisms. And therein lies their effects. So what we did is we showed, and this is with Lon Wilson in our chemistry department, we derivatized our materials to make them more water soluble, which I found counterintuitive. Shouldn't that make them more toxic? But in fact, it made them much less toxic. This is just one example of a 48-hour experiment looking at how many died. At a very low concentration, if it was the pristine material, a lot of them died. And you had to almost, couldn't go up to high enough solubilities with the water-soluble one. So that's, and we did the same thing for nanotubes and found if you want to make a safe nanotube, oxidize it, derivatize it, make it more hydrophilic, more water-loving. And then it dilutes in a very large environmental system and doesn't get concentrated into compartments. So rather than our engineered nanoparticles dangerous, it's how can we make them safely? And that was one example. So the last point I want to make is why was that hard? Why is it hard to do the proactive work on new technology? And my single reason that it's really hard is that our systems for funding and science in this country, if you want to make a better battery, you focus on competition. You make 4 teams and you say, go. You have 4 different ideas and they see who comes out with the best battery. It's kind of our culture. It's that part of that machismo, I think, that we were talking about. But if you want to know if the battery is dangerous, the absolute last thing in the world you want is to form 4 teams who are going to have 4 completely different opinions. And so when this culture gets into regulatory science, it just gums it right up. And groups fight and they, that's the nature of science. But the sense of community and rapidly moving towards consensus is not something that our scientific establishment just sort of naively is ready to do. And I think particularly in nanotech, where there's a lot of applications funding, it gets particularly challenging. So right now, there's not consensus in our community about what's dangerous and what's not for nanotechnology. Not surprising. But I think that makes it the hardest thing. OK, so those were the 2 points I wanted to make. I hope I get to interact with all of you. And thanks for your time. Yep. Great.
And she tested these nanoparticles on healthy cells and found pretty much similar to what you said about not only cause cell death, but they also activate autophagy. There's all kinds of things at the concentration that actually you can find in the cosmetic. So
Right.
And I read a little bit about it that the FDA actually approved using this compound in 50s, and when these nanoparticles, did not exist. So as I said, that these nanoparticles actually have very distinct properties.
Yep.
As the, FDA approved the last, half century ago. And so, what's your view about how safe?
Well, OK, here's what I do with my kids. I don't use sunscreens that contain zinc oxide.
Yeah,
Zinc oxide is actually worse than titanium dioxide, and we published. Well, the reason, and I have a whole talk on that. So you're right, the government regulatory standard is to regulate based on the composition of matter, not on the size. And the FDA has a 1999 ruling that set forth basically the definition for the ingredient lists, and they held up that a micronized particle is the same as a large one. There was an argument that nano is micron-sized, and therein, you don't know when you buy something if it's nano. I can tell you we've tested for Consumer Reports now 16 different commercial sunscreens in the US. All of them, if they say TiO2 or zinc oxide, they're nanoscale. If they go on your skin and they're clear, They have to be nanoscale pigments. And there's very dense residues that are left behind. Most of the manufacturers, not all of them, wow, I thought I had turned this on, not all of them, sorry. There we go, it's off. Most of the manufacturers coat the titanium dioxide so its photocatalytic properties are, oh, it's my timer. Okay. So I was like, it's a phone call? Most of the manufacturers, titanium dioxide, if you don't know, is a really photoactive substance. If you want to make oxygen radicals that like chew up paint and steel, you know, paint titanium dioxide that's uncoated, high surface area, nano, let sunlight hit it, and if it's the right crystal structure, this stuff will plow through metal. I mean, it's amazing stuff, and it's used industrially. It is the exact same materials and manufacturers that make the pigments for your sunscreens. So the really good ones, and there's only, most of them are good with TiO2, they coat the outside of the titanium dioxide, usually with alumina, and it's a thick enough layer that you lock off the surface chemistry, but you still get the high UV absorption qualities you want. So we found in the ones that we tested, there were 2 brands that did not do that. So they had raw photocatalytic materials in their sunscreens. It's kind of stunning, but in any case. But the other ones did. And the zinc oxides were less net reactive, kind of on a, you wouldn't use them as a photocatalyst maybe, because they eventually, over like several months, degrade themselves. The oxygen radicals go after the zinc oxide lattice itself, which in TiO2 that can't happen. So the zinc oxides, though, were not known to be photocatalytic. And so when we did our test and a few other groups did their test and we started to see the zinc oxide sunscreens show the very biggest effect on cells and have the biggest ROS producing capabilities, that was really surprising. And so that was kind of a shock to me. And I was happy that the manufacturers had at least coated their TiO2, but I was very disappointed that, you know, they're also selling zinc oxide that's uncoated. So I don't tell people not to use sunscreens, but, you know, because it's a risk benefit. You know, there's a known risk of not having any sunscreen on at all, although I had a smart person there tell me, sorry, it's the timer again, telling me to be quiet, be quiet. Say, why don't you just wear clothing? And in fact, that would be the safest option, although who wants to run around on a beach, you know, in a log? So, you know, I think that it's a really interesting question. What I'm waiting for is somebody to really put, you know, to look at some of the epidemiological data. You know, there's been a huge increase in the sun care market. I mean, it's billions and billions of dollars across the world. So you would expect, usually when there's a treatment that's useful preventively, you see an impact on cancer rates. And they haven't seen that yet. So there's a big dialogue right now going on about why is, you know, is it just that more people are outside? Is it that the, you know, UV radiation is changing? Or, you know, the dermatologists are saying maybe our sunscreens are not effective, maybe people don't apply them enough or something like that. But there hasn't been an epidemiological response to the huge market increase in the use of sun care projects. So use them, but be aware that, you know, maybe don't use zinc oxide on your kids. So that would be my editorial that is on no basis other than, you know, my own data. So it's a great question, and I think, you know, you wonder, it's an interesting governmental question. How should you regulate emerging tech? Should you wait, or should you try to do it quickly? And right now it's very open. I would not say it's an over-regulated environment. Great. Sorry for that long-winded. Got me on something I really wanted to talk about. Thank you.